In exercise 810, they're asking us to draw the mechanism for E1 reactions. Now we know that for two reasons. In the exercise it says elimination, okay, so E, and then it says a stepwise process. That's a process that happens one step at a time. So only one thing will ever happen at a time, and that's what the 1 in the E1 is talking about. And when I say thing, I mean movements of electrons. In elimination reactions, you have two standard movements of electrons. You have the loss of a leaving group, and you have proton transfer. Now, in E1 reactions, these two will happen separately. They'll happen one at a time, and that's what the 1 in the E1 is talking about. Now, similarly to SN1 reactions, because you have loss of a leaving group first, you end up forming a carbocation intermediate. And anytime you form a carbocation, you could get carbocation rearrangement. So that's a different feature that you have to consider for E1 reactions. And the last thing is, because the first step, the loss of a leaving group, because the leaving group is not getting pushed off in this case by a strong base taking a proton and having the electrons to that beta hydrogen push the leaving group off, as we've seen in the last couple of videos, because the leaving group isn't getting pushed off, but rather is just leaving on its own, it needs to be a good leaving group. And so the first thing you want to do when you're drawing these E1 mechanisms is to check, do you have a good leaving group? If not, then you have to do a proton transfer. So, in other words, you will always have loss of a leaving group and proton transfer. They're just the staples of an elimination reaction. That's how you get the reaction done. For the carbocation rearrangements, for these E1s, you now have to watch out for those. It's easy to forget those, but they can be there because you form these carbocations. And then finally, you have to consider at the very beginning if you need to do a proton transfer to turn a bad leaving group into a better one or a good one. So here, you'd only have to do this step if you have a bad leaving group. And the most common bad leaving group that we have is an OH. So if you see that, for sure, you would want to add some sort of an acid, do a proton transfer so that it turns into H2O, and then it's a good leaving group. Okay, so those are our possible steps. So let's see, before we dive in and try to draw the actual mechanism, let's just see which ones we need to do. This way we'll make sure that we don't leave anything out. Well, we know for sure that we have to do loss of a leaving group and proton transfer. How about carbocation rearrangement? If you're checking on that, redraw the reagent, the original molecule, and instead of the chlorine, or instead of your leaving group, add a positive charge. That's going to be your carbocation. And then think, would that carbocation rearrange? Well, it is tertiary. This carbon that has the positive charge on it is bonded to 1, 2, 3 other carbons. And next door, you'd have a primary position, and another tertiary position. But it takes energy for a hydrogen to move over and for the carbocation to rearrange. So unless there's a more stable position nearby, the carbocation won't rearrange. And so here you don't get carbocation rearrangement, so you don't have to worry about drawing the curved arrows for that in this case. And then finally, in the very beginning, check to see if you have a good or a bad leaving group. We have a chlorine. Chlorine is an awesome leaving group. The halogens in general, except for fluorine. The other halogens are really big. Chlorine is the size of a methyl group, so they can sort of spread their negative charge out and dilute it and stabilize it that way. So we have a good leaving group, so we don't have to do a proton transfer to turn it into a better one. So we're just going to have the two standard steps here. Okay, we're going to do the steps separately. So we'll redraw our molecule. And the first step is going to be loss of a leaving group. So leaving group takes its electrons and hightails it off of the molecule. So now we have just the two methyl groups left there. Remember, carbocations are trigonal planar, so I'm drawing that as a trigonal planar. And there's our carbocation, and we've already done the analysis on this. That's a tertiary carbocation. There's not a more stable position nearby, and so that carbocation does not rearrange. So we just do our next proton transfer, or we do our next step, which is the proton transfer. Right? We don't have to worry about carbocation rearrangement. So, proton transfer. Well, what is our base? Our base is water. Water is a very weak base. It's pretty stable on its own. And this is a trend that you'll notice when you compare E1 reactions to E2 reactions. E1 reactions will tend to use weaker bases. E2 reactions will tend to use stronger bases. And that's because in the E2 reaction, the base is participating in that rate-limiting step. It's helping to kick the leaving group off. And so if you have a strong base, that helps that process out. If you have an E1 reaction, the leaving group is already left. This positive charge is aching for some sort of electrons to help stabilize it. And so it doesn't take a lot to pluck a beta hydrogen off. Remember, the alpha carbon is the carbon that had the leaving group attached to it. Each carbon that's next to that alpha carbon is a beta carbon. So we really have 3 beta carbons here. And the hydrogens on the beta carbons are beta hydrogens. Now the base is just going to take one of them off in this example, and so to know which one it's going to take off, look at the product. The double bond is going toward the ring. That means that the hydrogen that's going to get stolen is going to be the hydrogen on the ring, on the beta hydrogen toward the ring. So I'm going to erase those others so that they don't confuse us. And so that full positive charge in the carbocation really wants to steal these electrons from this hydrogen. So you don't need a strong base to try to pluck that hydrogen off. Just a small tug, and the electrons will snap, going toward to form a pi bond toward the carbocation, toward the positive charge. Now notice, this is not going to the carbon. That arrow is going to form a pi bond. Okay, so in that case, we have our product. And so you had the same 2 steps that we saw in an E2 mechanism. You had loss of a leaving group and proton transfer. But in an E1 mechanism, they happen separately. They happen one at a time. So we're going to use the same process of thinking when we analyze these next E1 reactions and we want to draw them. Okay, first step, let's just see which of these possible steps in the E1 reaction could happen. Well, we know for sure that loss of a leaving group is going to happen and proton transfer is going to happen. Otherwise, it wouldn't be an elimination reaction. Now let's think about the carbocation. Redraw the reagent, but draw it where instead of the leaving group, you have a positive charge. So carbocation. What type of carbocation is that? Will that carbocation rearrange? It's tertiary. The carbon above it is primary, to the left secondary, to the bottom secondary. So the carbon that carbocation is on is already the most stable carbocation. So the carbocation won't rearrange. It's already its most stable self, so we won't have to worry about that. Then let's look at the leaving group. We have a bromine. Bromine is an awesome leaving group. The halogens in general, except for fluorine, are really big, and so they can spread the negative charge out, dilute it, and stabilize themselves. And so we have a good leaving group, so we don't have to do a proton transfer to make it a good leaving group. It's already a good leaving group. So in this one again, we're only going to do those 2 essential steps, loss of a leaving group and proton transfer. So here, we'll redraw our molecule. We have our leaving group there. Our first step that we have to do in this one is loss of a leaving group. So the electrons pop off. They pop onto that bromine. Bromine hightails it out of there. So now we have bromine floating somewhere in the solution. And one way you might see that is sometimes they'll say minus bromine. And that just means bromine's somewhere in the solution. It's not really part of our story. It's not part of the story we're following anymore, which is the story of this carbon chain. So we don't really pay attention to it. But okay, so the bromine comes off. We have that carbocation where it was. That carbon is now missing the electrons that bromine took with it. We saw that you don't get carbocation rearrangement in this particular case. The carbocation is already its most stable self. And we have methanol. Now, that Me, remember, is a CH3, and then OH. So you could also draw this as that. Now, methanol is a convenient time, I guess, to talk about alcohols. Water is around 3/4 of our planet, huge amount of water, and so you can imagine that in the course of the history of the Earth, carbon molecules have run into water a lot, and they've bonded to the oxygen. You can imagine that if you replace one of those hydrogens in water with a carbon, you end up with something that's really similar to water, but now it has a carbon on it. Well, the top molecule is water. The second molecule is classified as an alcohol. Before you took chemistry, alcohol was just one thing, drinking alcohol. But now you'll see a richer world. There are truly an infinite number of alcohols. This carbon chain could be anything. But so long as it has the OL there, so long as it has the OH there, it is an alcohol. And so the suffix for an alcohol is an OL. Otherwise, the naming is the same. So here we have one carbon, so meth, all single bonds, so AN, and it's an alcohol. We have the OH, so we have OL. The OH there is this OL. And you'll recognize that ending OL from some famous molecules, like cholesterol ends in an OL because it has that OH there. And ultimately, alcohols are derivatives of water. Okay. Now, I just say that not because we're going to be naming alcohols, but just because we're going to be using alcohols sometimes as weak bases, and I want to be able to use the names for them. So I just wanted to introduce that there. So here we have methanol, and methanol is a weak base. It's already stable by itself, kind of like water in the last example. After all, it is a derivative of water. Actually, do this. And so we can have that weak base because there's something on the molecule, the carbocation, that really needs to be stabilized. That's trying to steal electrons from all around itself. So it doesn't take much of a tug for that methanol to pull off the beta hydrogens. Now remember, the alpha carbon is the carbon that has the leaving group on it. So if we follow, that's that one. The beta carbons are the ones next door to that. Now we have 3 of them here. We have one to the left, we have one to the top, we have one on the bottom. Now to know each of those have hydrogens, to know which one we're going to pluck a hydrogen off of, we want to look at the product. You can see the product is going down, so we're going to steal a hydrogen from the beta carbon going down. So that has 2 hydrogens on it. I'm just going to draw one for the sake of clarity, because only one is going to take part in this reaction. So it doesn't take a large tug. These slightly negative oxygen can tug on that hydrogen, and these electrons are already being pulled toward the positive charge, so it just takes a small tug, and there you get that proton transfer. The methanol steals the H+, and the electrons that were keeping the hydrogen on the molecule go toward the positive charge, the carbocation. And that gives you your product. And here. Now you also have a protonated methanol floating in solution. But again, kind of like with the bromine, that's not our business. We're following the story of this carbon molecule, not all of the rest of the stuff in the beaker. We're only concerned with that when it changes the carbon molecule. So here's your SN1 reaction. Standard SN1 reaction, a basic SN1 reaction, just has the 2 essential steps: loss of a leaving group and proton transfer. Okay, let's try to do that one again with C. Okay, so our thought process is going to be, we're going to go through that same thought process. We want to consider each of these possible steps before we start drawing. This way we never get lost and we never forget one of our steps. Okay, well, we know for a fact we're going to have to do loss of a leaving group and proton transfer. It's an elimination reaction, period. Even if they didn't tell us, we see a leaving group that's not there anymore in the product, and we see that we form an alkene. Those are the staples of an elimination reaction. So loss of a leaving group and proton transfer for sure. When we want to think about carbocation rearrangement, redraw the molecule, but instead of the leaving group, draw in a positive charge for carbocation. And think, would that carbocation rearrange? Well, it's tertiary right now, and next door all of the carbons are primary. So it's already on the most stable position that it could be on. So it will not rearrange in this specific example. We will do examples where we have carbocation rearrangement, but we're not going to do it here. Then, with proton transfer, look at the leaving group. We have an amazing leaving group. Iodine is not only a halogen, it's the biggest of the halogens. It's a monster atom. It's gigantic. It can spread the negative charge over itself and dilute it a lot so that to stabilize it. So that's going to be awesome. That can take electrons and stabilize their negative charge after it leaves the molecule. So we have an amazing leaving group. We don't have to do a proton transfer to make it a good leaving group. It's already amazing. So again, here we just have those two essential steps, loss of a leaving group and proton transfer, but they're going to happen one at a time. So let's draw that original molecule. And the first step is loss of a leaving group. So the iodine takes its electrons and pops off. Oops. Now what we end up with there is a trigonal planar carbocation. You'll see there's still the same number of carbons, 1, 2, 3, 1, 2, 3. I'm just drawing them so that they're trigonal planar. That's the shape of a carbocation. We saw already that this carbocation is not going to rearrange. It's already on the most stable position. And so all we have to do, all we have to do is treat it with a weak base that will steal one of the beta hydrogens. Okay, well, let's look at our base. Our base is an interesting molecule, ETOH. The ET is an ethyl group, so CH3CH2, and then OH. Now, notice that that's another alcohol, right? It's that derivative of water. Replace one of the hydrogens in water with a carbon, and you get an alcohol. The suffix for which is OL. So if you were going to name this, you have two carbons, so Eth, all single bonds, so AN, and it's an alcohol, so OL. This is ethanol, it's drinking alcohol, which they also add to things like hand sanitizer or gasoline, but it's the alcohol that's responsible for getting you tipsy in beer or wine. In this case, though, it's going to be acting as a base, and it's going to be stealing some beta hydrogen, a beta hydrogen. Now to think about which one, or I should say, notice the carbon that has the leaving group on it is the alpha carbon, so that's this one with the carbocation, and each carbon next door to that is a beta carbon. So here we have beta, beta, beta. Now, the base is going to steal a hydrogen off of one of those beta carbons. It's going to steal a beta hydrogen. And if we just want to be strictly consistent with the molecule given above, we can take the beta hydrogen off of the bottom left. Now, technically, this molecule is symmetric, so you could take it off of anywhere, but why not? We'll take it off of the bottom left, so it looks the same as what we already have written in the exercise. So the lone pairs on the oxygen of ethanol, the oxygen of ethanol is slightly negative, right? The carbon and the hydrogen bonded to it are slightly positive. So that oxygen is slightly negative, it attacks this hydrogen. The electrons in that hydrogen are very vulnerable. They've been trying to get pulled toward that positive charge this whole time. Well, now they can do it. They go toward the positive charge, and so we end up getting our product. Notice again, ethanol is not a very strong base. It's stable by itself. It doesn't have a full negative charge. But this molecule does not need a very strong tug to get the hydrogen off, because the positive charge wants the electrons for itself already. So that weak base is a signature of an E1 reaction. And so this is the full mechanism for this E1 reaction, this basic E1 reaction. We just had loss of a leaving group, and then proton transfer. So hopefully this clarifies a little bit how you would start to think about drawing the mechanisms for E1 reactions.